All right, students, welcome in. Welcome to week 12. So we are going to be discussing magnetism this week. It's one of our forces in the universe. We have, the force of gravity. We have the strong and weak nuclear force, and we have the electromagnetic force, which is why we're going to dive into magnetism. It is a common thing that we see every day. Magnets on our refrigerator. We can play with them, and they're very fun to, kind of just play around with. But we want to understand, why are some things magnetic and what makes them magnetic. So let's go over a few things first. First off, this is our course page. We're all familiar with it now. If you click on our course and you scroll to the bottom, we see the week 12 module. And so we can get right into that. If I click on it, you're going to see, the very familiar four sort of subjects here that we will go through. So the first one, as always, is just our discussion board. So this one's on magnetism. And so we have a video attached to it. And this one discusses Earth's magnetic field. And you'll learn about this on CK12. But this will give you a good primer. Like, it's good to get you sort of almost like jumping into the pool before you can swim. Like you're jumping into the shallow end here, just so we can get used to the waters. And then once we understand more material from the lecture and from CK12, we'll be able to swim with it. So the video is a little dry. The guy is not very charismatic with how he talks, but he gives great information. And it gives you an idea of how important Earth's magnetic field is. Without it, we'd be subject to solar winds that could wipe out life on the planet. If you've ever heard of the auroras, like the northern and southern lights, the reason we have those is because of our magnetic field. So much so, it spans out from Earth that we call it the magnetosphere. And that's one of the questions you'll see later on in the CK12 unit. So just the two questions here after the video is, what is the difference between Earth's magnetic pole and the geographic North Pole? So you'll find that what we consider to be the North Pole, just based off of how the Earth is in space, is not the same as where the North Pole is magnetically. Meaning that if Earth's geographic North Pole was like a straight up and down, so here's south, here's north, the magnetic pole is tilted slightly to where this is the northern end, where the magnetic field comes out and goes back into the southern end, but it's a little bit tilted from what true north, or I should say what geographic north actually is. And so this will tell you why. And it's pretty interesting. They show you how the magnetic poles reverse from time to time, and also how the magnetic North Pole wanders. And we don't 100% know why. We have a magnetic field. They believe it has something to do with the movement of fluids in the core, or in the outer core, like the nickel and the iron. And we'll get into that a little bit more at the lecture. But so that is the first part of our module for week 12. So if we go back to our modules, and all of them are still here, so you can still, catch up, do the work. I implore you to do the discussion boards. A lot of people aren't, and you are going to lose up to 10% of your grade for that. It is something that is not an correct or incorrect thing. You just have to answer the question and you get full points. So don't let those points go by the wayside. So here's the link to our ck12.org work. And so if we go there, and if we look, if you go into November, we have our week 12, our magnetism. You're going to notice, similar to last week when we click on it, only 3 sections and no quiz. I'm trying to give you, and this will be the last week I'm able to do this. Next week, we got to hop into the quizzes again. But I'm trying to just get you up to date with things conceptually, rather than have like a quiz at the end. I'm hoping that by doing that, I will give some of you who have not caught up fully with CK12 some time to get the other ones done. But we just have 3 sections, just magnets, Earth as a magnet, and why is Earth a magnet. So some of you may be with me next semester for Earth Science, and this will be a good primer for when we discuss this when it comes up in Earth Science. So just those 3 sections, and like always, when you click on it, you're going to have an article to read. There's videos and real-world examples, and your adaptive practice. So you'll want to do all of those. And so the lecture that accompanies this unit as well will help you to progress those units very easily. So just those 3 sections and no quiz. So I'm kind of giving you a break last week and this week without a quiz, but don't rely on that, because next week the quizzes will be back and the units might be a little bit longer when we get into the last few topics. And so I say the last few because this is week 12. And so after this, we only have weeks, 13, 14, 15, and 16, and then we're done. So if you're not caught up on CK12, don't put it off to the very end. I would start to make sure you get caught up on that, put in some extra time, because when you get to the very end, there is a hard close date for the end of the semester. And anything past that, it can't be accepted. And we'll get to that a little bit later on. So now, going back to our module. So by the time you're watching this, you'll know that the lecture is in here. And here's our magnetism and PowerPoint without the lecture. So this will always be here for you to go back and refer to. And that's what we're going to hop into now. We're just going to get right to the lecture. I'm going to try to keep this video nice and short. So we're going to be talking about magnetism. Whoops. Actually, I'm going to close out of this. Actually, let me just hop back one slide. And so talking about magnetism, we are used to magnets as such, these little horseshoe magnets or the magnets that go on the refrigerator. But we want to know why. Why are these things attracting other materials? How come if you put two northern ends of a magnet together, they'll repel, as opposed to north and south attract? Why is that? And it has to do with spin of electrons, and we'll get into that. So first off, what are magnets? That is an important thing to start with. And we want to talk about what causes a magnetic field. And so a magnetic field is created around any moving charged object. So you have to think about way back in the semester when we talked about electrons. When we talked about electrons, I kind of said they kind of rule the show, not only in chemistry, but they have implications for other parts of science as well. And this is one of them. A moving charged object is going to be the electron. The electron has that negative charge, and it is moving. It is not stationary within that nucleus. So it's a moving charged object that will create a magnetic field. And so this here is just a regular bar magnet with a northern end and a southern end. And if you put iron filings around a bar magnet, it will outline the magnetic field for you perfectly. So you can see how some of these lines are coming out of the northern end. They kind of arc across and go back into the southern end, and then sort of repeat that way, going out of the northern end into the southern end. And that's the movement we'll always see. And let's get into that. So magnetism, it is a force of the universe. And it could be an attractive force or it can be a repulsive force. But just like gravity is a force that pulls us to Earth, and the nuclear force holds the protons and the neutrons in the nucleus, magnetism is just another force that we have in the universe. So it is the force of attraction or repulsion between magnetic poles. So when we think of a pole, you have a top end, you have a bottom end. So if we think of poles with magnetism, we have a northern end and a southern end. So if you were to have small magnets like this and you were to try and bring the north and south end together, they attract each other very strongly in some instances. But if you try to reverse that, if you try to put the two northern ends together, they'll repel, they'll push each other away. And same thing if you try to do the same with the southern ends. If you try to bring the southern ends together, you'll have that almost invisible force. I shouldn't say almost. It is truly invisible force that pushes them away from one another, as opposed to the invisible force that would attract them together if you have opposite ends. So what is it that is charged, that is moving within an atom? It's the electron, what we talked about before. There's only two charged particles within an atom, and that's the proton and the electron. Well, the only one that's really free to move is the electron. So the electron is going to be responsible for this. As it moves through or around the nucleus, that is the moving charged particle. So the atoms with the most material have paired up electrons spinning in the opposite direction, which usually cancels out their magnetic field. So most material, their electrons have been paired up. So when we said they've been paired up, if you have one spinning one way, one is typically spinning the other way, and that sort of cancels out any sort of charge that can be built up within that material. But when that's not canceled out, you have some materials like iron, nickel, cobalt that have a single electron or a pair of electrons that are spinning in the same direction. So there's nothing to cancel them out. So as they're spinning in that same direction, they create a magnetic field. And technically, this would be, if you just look at the atom itself, it would be like a tiny atomic magnet. But if you get enough of these materials together, then we can have, or I shouldn't say charge, massive magnets. You have magnets that can lift cars. You have stuff like, if you YouTube neodymium magnets, you're going to see some of the strongest magnets on Earth that could crush a hand if it was between these two magnets. That would be almost impossible to separate just using regular methods like pulling them apart. So, and let me hop back to that one, because when we're talking about the Earth and the Earth's magnetic field, the material that makes up the mantle and the core is mainly iron, and in the core, nickel. So if we have molten iron and nickel spinning around as the Earth does, that's very similar to this electron spinning around, creating a magnet, and an invisible force, if you will. So that movement of material within the Earth is probably what causes Earth's magnetic field. And it's one of the most important things that keeps life on Earth, an option. But it's also not something we understand very much. So it's an interesting subject. So the atomic size magnets, so all those little atoms of like iron, nickel, cobalt, they will line up and they'll create what are called domains within the material. And then those domains will start to point in the same direction. And when all those domains line up, we get a typical bar magnet with a northern end and a southern end. And so the magnet will always have that northern and southern end, and those are each called their poles. So with the magnets, we can call them a dipole. Di meaning two, and then poles, meaning a northern pole and a southern pole. So those are the areas where the magnetic field is the strongest. So you had all those domains lining up to sort of push out those ends, and so that's where it's the strongest. And the cool thing is if you took a magnet and you chopped it in half, you didn't just separate the northern and southern poles. You now have a new northern pole and a new southern pole. So no matter how many times you break a magnet, each piece will always have a northern and southern pole. There's no such thing as a monopole. Mono meaning one. There's no such thing as a magnet that just has one pole. So the magnetic fields become pretty interesting. They exist around a magnet or any moving charged particle or object. So it could be a particle if it's, an atom, or an object if it's, a horseshoe magnet or a bar magnet, or even the ones that are put on your fridge. So these magnetic fields, they're like electric fields. They are the same as gravitational fields. They are stronger in certain places and weaker in other places. In that, but they're also similar in the fact that they allow magnets to interact without touching. So you can slowly bring two magnets together, and then when they get to the point where that force builds up, they will interact without touching. They'll come together without you having to do anything. And they can interact that way. Same way if you try to do the north end and the north end of two magnets together, if you tried to slide one next to each other, it would repel the other. And so they're able to interact without touching, which is a pretty cool thing. That's an amazing thing about magnets. So the rules for drawing magnetic field lines, which is the same as electric fields. So, and I know we didn't talk too much about electricity yet. We will get into that within the next few weeks. But magnetic field lines, and you'll see some of this in your CK12 work. That's why I wanted to touch on this. They always go out of the northern end of the North Pole and then down to the South Pole. So you can see here, they're leaving the northern end, going all the way around down into the southern end. And those domains that are lined up in there are pushing that force along. If you have a bar magnet here, once again, coming out of the north, going into the south, going from the north into the south. And we can build up these lines that sort of denote the magnetic fields. And this is really important when it comes to navigation. Now, nowadays, we just all use GPS, Apple Maps, Google Maps, Waze, whatever it is. But back when you didn't have that and you were relying on a compass for navigation, that compass relies on the magnetic North Pole. And so the movement of that needle is moving around based off of these magnetic fields. And so if you want to draw some of these, magnetic field lines, they're always going to be closed loops. They're never open and just going off into nowhere. They may go further out, but they will always still stay in these closed loops. And the ones that are closest and smallest, I should say closest to the magnet, and they are the smallest closed loops, they will be the strongest. But it is important to note that these loops never cross or intersect. They are individualized, they are on their own. So where the magnetic field lines are closer to the magnet is where the magnetic field is stronger. So you can see in this diagram here, on this graphic, if you will, these are the magnetic field lines. And the ones that are closer to the magnet here, the ones that have like these smaller loops, that's where the magnet is strongest. And that's where it will exert its most force. So if you brought something that was metal, and say if it was over here, like where it says magnetic field lines, it will feel the pull of the magnet, but it's not going to feel it as much as if it were closer. If you brought that a little bit closer, it might just tighten up to the magnet and stick to it because of the attraction there. But if you're further out, it may not. Well, it may move a little bit, but the attraction won't be as strong. So let's talk about Earth's magnetic field, because you do have a section on that in your CK12 work. So you have the North Geographic Pole and our Southern Geographic Pole, which we said, it is not the same thing as our magnetic poles. So it's hard to see in this picture here, but there's a little red pole at the top and a little red pole at the bottom that's showing our geographic poles. And that's just where, as the Earth is in space, our northernmost point and our southernmost point, which is based off of the geography. But the magnetic pole is slightly off center of that. And so that's what we call, our magnetic pole, or sometimes these can be referred to as true north, as opposed to, to the North Pole. But you can see it's the same thing. The magnetic field lines flow from the north going into the south, flow from the north going into the south. So as you saw in the video, hopefully you watch that before you're getting into this, you'll realize from there that we don't 100% know why the Earth has a magnetic field. We have hypotheses and we have really good working theories, but since we cannot get into the center of the Earth, we cannot say for sure. But we do know that the North Magnetic Pole and the geographic North Pole do not coincide. And if you watch the video and you saw like how it sort of spins and rotates over time, you'll know that it's not lining up 100%, but over time it sort of marks the true area. And so a compass will indicate the direction of the magnetic north. So if you have an old school compass in your hand, and the way that it points, it's pointing towards magnetic north, but not true north. True north would be where it is on our geographic globe, if you will. So if you were a navigator in the backwoods, or if you're hiking around, you would need to sort of know the difference, like how far it's going to go. And you saw that in the video, how far off true north is from magnetic north, and then they have to adjust the compass for what's called declination. And the angular difference between the magnetic north and the true north is what we call declination, and it varies across the globe. So just because you adjust your compass to point to north up here in California, if you were down in South America, or if you were over in Australia or in Europe or anywhere else, you would have to adjust it on a different scale because the declination would be different. And so the details and the mechanisms of how and why Earth's magnetic field wanders, why it changes, why we have it, that's still all very unclear. But because we know that the material within the Earth is most likely molten iron and nickel, and if it's spinning, and if it's all spinning in the same direction, it kind of gives us an idea of why we might develop a magnetic pole. All those, like we saw, the electrons spinning in the same direction create the magnetic force. Well, if all this material and this liquid, metal is spinning in the same direction, it could develop, a magnetic field. And that could also be a reason why it adjusts over time or wanders over time. Maybe that fluid, changes the way that it's circulating around in there, and that moves the magnetic field. But once again, we don't 100% know. And so this was just meant as a primer for your CK12 unit. This is the end of the video. It's the end of the lecture, so it'll be a short one. So make sure you are doing the discussion board. Make sure you are doing the CK12 work, and let me know if you have any questions whatsoever.